Okay, the next step is to start looking in detail at some of the operations topic. We'll look into the cache first, see what it's actually doing. We'll identify some of the diagnostics that are important for running the server, and we'll, well, you know about the SNMP agent already, so you know how that works. It's exactly the same way, so there's not much to say there. And we'll talk about some of the defenses against vulnerabilities, specifically the spoofing defenses. So the first topic is around how the operator can determine what CACHESERVE is doing and whether it is operating in an optimal way. So I mentioned in the introduction that if we assume that there's no I/O restrictions, specifically the network is not a limitation. In other words, it's the network itself or the network stack on the machine is able to keep up with the capacity. That there should be no I/O due to disk access, because CACHESERVE doesn't go to the disk hardly at all. I mean, it certainly does when it starts up. It has to read its database, and there are occasional, if there's a change to the configuration, there will be a journal, a log file that's written to the database, on the on-disk database, but that's about the only thing that you would have. So it's really the CPU which is going to determine, it's going to be the limiting factor in how many queries per second that the server can handle. So we'll talk about the constraints there, which are partly in the license file. So the license file is what determines how many CPUs you can use. If you have more CPUs, you'll be able to get more queries per second from the server. And we'll look at the commands that you use. I'll give you a hint. It's called server.usage. That will tell us which threads are taking up the most CPU. Most CPU time is how it's actually measured. So the other thing that we'll look at is memory. Again, we don't care about on-disk memory. We're talking about memory of the process, and there are two components there that make up the memory footprint besides the code, the process itself. There are two major users of memory. First is the cache, or if you have multiple resolvers, there will be multiple caches. So that will consume memory. Up to 1 gigabyte is the default. Of course, people have a lot more memory on their machines than they used to. So you can increase that default size. We don't necessarily recommend it unless you know that there is some benefit to increasing the cache size. In other words, if expanding the cache size increases the hit rate, and we'll show you how to measure the hit rate on the cache. So if the cache is becoming more efficient by making it bigger, then yes, you can make this bigger, the cache bigger. So we'll talk about how to do that. Recursion context. This is also a consumer of memory. This expression, or this terminology is shared with bind, with named. It's the same idea. and it represents the space in memory, which I like to think is the kind of a scratch pad, a kind of an accounting information that CACHESERVE needs when it's doing a lookup to an authoritative server. So a recursion, I consider a recursion is like a lookup to the outside world, and CACHESERVE has to remember things about which server it sent a query to, how long it's expected to wait to get a response back. All of that kind of stuff takes up some memory. So every time we launch a recursion, there is additional memory that's consumed. So these are the two places where CACHESERVE uses memory, and there are limits on how much memory they will consume, because left unbounded, the cache or the recursion context, either one of them could just fill up exhaust a machine's memory very quickly. Under a situation where there's an attack, it would be a very bad situation, because you could easily find yourself in a situation where the server is broken completely. And that certainly has happened with bind before. It doesn't happen with CACHESERVE, but these have limits. So we'll talk about those. We'll talk about what goes on here, and then we'll look more at the statistics, tools for viewing the statistics easily, and then we'll look at this cache hit fraction or cache hit rate, which I mentioned in response to this cache size, evaluating whether this cache is big enough. We can use this number to guide our decision making on making the cache size bigger. Okay, so we'll start with the cache memory. And in order to describe this, I like to appeal to a kind of schematic diagram, which, again, the engineers laugh at me because this is not exactly how it works, but it's a useful illustration of the cache. And so this entire set of things, these individual lines, represent DNS data in the cache. So it's information that has come from authoritative servers somewhere on the internet. So each one of these little lines represents some data. And so there's some maximum size of the data. By default, the max cache size is 1 gigabyte, as I mentioned before. If I want to change that, and the value of doing so may or may not be high, because what you end up storing in a super large cache are a bunch of entries that will never be requested again. There is a lot of junk in the DNS world that is not useful for customers. There are outright attacks. There are exploits that use DNS for tunneling for data connections. There's just a lot of garbage floating around. And so what you end up caching, if you make this especially large, is a lot of junk that does not help anybody, and it just simply consumes memory. So we don't recommend increasing the size, but out of the box, this seems like a good number based on our studies of typical traffic. Again, individual results may differ. Okay, so each one of these lines represents some data. What do I mean by the data? Well, let me go into the server. If my server is still running, yeah, he is. I'm going to fetch spooner.com again. You can see this used to be 14,000 seconds. Now it's 11,000. So it's decreasing still. So that's still in the cache. It's not going to disappear anytime soon. Let me ask for google.com, something a little bit more interesting. So that is now in the cache. We can see this is a fresh answer. I just recognize the nice even number suggests to me that this probably came from the cache. I could ask CACHESERVE about it, and also the query time is pretty fast, so I can't tell from that whether that's been required a resolution or not. But anyway, this is an example of a thing that you would see in the cache. And if I wanted to see that nomtel CACHESERVE, I can look at the cache by using a resolver command that is called inspect, and then I give the name of which resolver's cache I want to inspect, which should be world, and then let me look for, what did I ask for? Google.com. Oh, I forgot the domain. Domain equals Google.com. This is we're not being very careful about the use of domain here. Domain in this context doesn't mean give me Google.com and everything underneath it. So in other words, it's not star.google.com, but rather this really should be FQDN or domain name or something. We don't really mean domain here, so we were not very critical about how we named these things. But anyway, you can see that when I look in the world resolver, and what I'm specifically looking at is the resolver's cache when I do this, we can see that the domain name google.com exists. True, it exists. And there may be some DNS data that's associated with that. And we can see that there is an A record that exists, and it has the TTL of 183 seconds, so it's continuing to count down from that 300, which it was originally. And then we can see that we have data of the resource record data. So this is a resource record set that has all these IP addresses in it. So these are the A records. And then we have this other little handy piece of information that identifies the origin of that information of the A record. This is the IP address of the name server that gave us that data, which for troubleshooting is going to come in really handy. So that's also stored in the cache. So you can see that these things take up memory. So all of this information is part of what goes into each of these chunks here. So in a training environment, I will have only a small portion of this maximum cache size that is actually used. I can ask my CACHESERVE how big the cache currently is. If I go to resolver statistics, name is equal to world, and I believe in here somewhere there was memory in use. So we can see that this resolver is taking up 55 meg. So this tiny fraction of this entire pipeline worth of stuff which is used. Now, let's imagine that the data is organized such that cached information that has been recently used is put here on the left-hand side. So say that google.com, 300 seconds ago, I asked for google.com, and that was recently used, and so that would be over here on the left-hand side. And then we just filled this thing was filled with information as the data comes in, and on the right-hand side we have data that hasn't been touched in a long time. So some resource record that somebody asked for once and has not asked for again. So that's arranged so it's on the right-hand side. So what will happen is this pipeline will just continue to just fill up and fill up and fill up until eventually we reach the maximum size. In the training lab, it may never happen, but in the real world, it will happen very quickly. In a production environment with tens of thousands of queries per second, it will happen within seconds that the cache will fill up completely. And when that happens, the oldest data, that is the least recently used, is going to drop off the end. So if nobody has touched something for a long time, it goes away. So that'll be dropped. And then that will give room for new results to be added to the cache. Now, some of this data, while it's sitting in the cache, it may expire. And that I've indicated in the red lines here. So I've got this red that indicates that's expired data. So even recently used data can be over here can be close to expiration or expired or close to expiration. So that's why it's got some of this data here which people have been asking for, but it's been expired. So scattered in here, you're going to find that there's some expired data, and we can see that in the cache. If I go back to my CACHESERVE, clear the screen so you can see this. I'm going to go back and look at google.com again, and you may notice a different response now. The resolver, the cache, still knows about the name google.com. In other words, that name is still in the cache. However, there are no valid records associated with it. So there's still some space taken up in the cache by this information here. And in fact, in memory, the data is there. It's just been marked as expired, so we don't see it anymore because it's not usable. But there's still some memory taken up by this. So that's why these red lines here are shown as taking up space, because they still do consume space in the cache. Now, if CACHESERVE needs some new space that can and it can fit into one of these red lines, it will overwrite that existing space. So the way this works is very similar to the way, well, maybe a disk drive used to work. I don't know if it still does this way, but when you delete a file, for example, in your file system, unless you have some like a military computer or something, the data actually isn't erased. It's just marked as deleted, and that space on the disk can be used by the system later on, but there's not actually a process that actually removes the ones and zeros from the disk. And that's sort of the way that CACHESERVE works, is it leaves this content on the cache. The space is available. It can be overwritten, just like with a disk. It can be overwritten, and that space can be used. But there is no separate process that goes in and checks to see, oh, here's something expired. I'm going to take this out of the cache. In that sense, there's some economy. It saves extra work of something going around and removing things. But it also has another implication in that there's no measurement of how old things were when they got removed from the cache, which is sometimes you may hear customers ask about that. Is there any way to know how long something sits in the cache before it falls out or something like that? So there is no process that is measuring that. That's simply for efficiency. Other products may have something like that, but that's because they have another process or another thread or some other resource that is looking in the cache and actively maintaining it. So there's no real active maintenance taking place on the cache. It's just opportunistic in the sense that data is being applied wherever there is space. And these red lines represent space that's available for the cache. So the cache will still be completely full most of the time, but I wanted you to see that if you ever look in the cache and you see something that looks like this, you will know what you're looking at. You'll remember, oh yeah, Spooner showed me the red lines. That's what that thing is. Then that's this remark here. For efficiency, the expired resource record sets are just marked as expired, and that space can be reused. The last thing I want to say about this is that a concept that is used again to reduce latency for popular names, and that is a prefetch. So this yellow line you see on the screen represents a resource record that is nearly expired. What does nearly expired mean? Well, AKAMAI has determined that almost expired means it's within 1/16 of its original TTL. So just to make the math simple, imagine that Google record that we saw, which original TTL was 300. Imagine the original TTL was 320. So 1/16 of 320, even I can do the math on that one, is 20 seconds. So this means what CACHESERVE is doing is that if there is a request for a name that is yellow, of course, things aren't really colored yellow, but yellow meaning almost expired. So if there's 20 seconds or less left on the name that somebody has requested, then what happens is that CACHESERVE will return the answer because the data is still good. It may be nearly expired, but it's not expired, so the data is still good. I should probably say the yellow line is then moved to the top of the line, the top of the stack or the left of the stack, because that's where data that's used recently goes. So in my comic book picture, the yellow line would go over here, but doesn't matter where the yellow line is. What the important thing is, the answer that is cached here goes back to the client. Simultaneously, a new request is made out to the authoritative server. So there's a new recursion that is started to go get a new copy of this data. The thinking is that if there is a request for this data, which has almost expired. That probably means that there are lots of requests for that name. And that means that it's probably worthwhile to go get a new copy because somebody else is probably going to ask about this pretty soon. So this prefetch is sort of a dynamic list of things, things that turn yellow in my comic book. So, but there is no list of popular domains or anything like that that are eligible for prefetch. The prefetch will just happen naturally for those domains that are the most popular. And so you will see there are statistics around this prefetch. And then, of course, the new data, assuming we get new data, it will go back into this space. It will probably turn, the yellow will go away because it's not nearly expired anymore. We've got a fresh copy. And then this will just sit in the cache, and presumably other clients will ask for it. So this is the cache. We'll have more to say about the cache later on because it turns out it's a little more complicated than this. But this is an easy picture to use. Any questions about the cache? Okay. Next stop for the other, well, actually, you know what? It is maybe break time. So this is fun, but maybe let's take a short break. I am going to. All right. So thank you for coming back quickly after the break. If there are any questions about the cache memory, put them in the chat, or you can respond to them now. Otherwise, let's move ahead and look at this other significant consumer of memory, of process memory that the CACHESERVE will use. That is the recursion context, and each recursion context represents an ongoing lookup to an authoritative server. It includes information about which queries were sent to which servers. Things like the query ID need to be remembered so that it can be matched with the appropriate response. The time it's taking to get the response back so that we know whether to move to another name server and hope that that one responds. And that kind of data all takes up some space, approximately 32 kilobytes. I didn't give any measure of the amount of space in the case of the name cache, because that depends on the size of the answer. So if the answer is huge, it can take up a lot of memory in cache. But if the answer is small, maybe it's tiny. That's one of the reasons DNSSEC is such a significant impact on the cache, is because the answers there, all of the answers for the keys and for the responses, that information tends to be quite large. And CACHESERVE needs to keep it because clients might ask for it, clients that actually do validation themselves. So anyway, so I didn't give any number about how big the cache entries were because it varies a lot. On the other hand, while this also varies, each recursive context is of about 32 kilobytes. So it's a good amount of memory. And so what we're seeing here, I've drawn another kind of schematic diagram to suggest what happens when a request arrives for which there is no cache entry. So this corresponds to the situation where a recursion is needed because we missed the cache, and this starts a new lookup to the authority. And on the left-hand side, we have the newly started recursions. And on the right-hand side, imagine that these are organized such that the longest running one is sitting on the right-hand side. And so there is some maximum amount of space in memory which is going to be allowed for this purpose. By default, I think the value is still 25,000. I could look in the man page and see what that is, but I think it's 25,000. The maximum that you can configure is 250,000, which corresponds to about 9 gigabytes. So it's not a huge amount of memory in a modern server has 64 gigabyte worth of memory or something like that, if not much more. And so this is not a terrible amount to put here. But but you can't make it any bigger than this, I think. And you can put in the number, you can put in, say, 1 million, but the server will not respect the value, and it will cap it at 250,000. So anyway, this size represents space effectively in memory. Each of these marks represents a recursion, and what will happen is that the recursions start piling up. If in general, it will hover around, I don't know, in my experience from what I've seen with the support guys, we see stuff that around 1,000 or something like that. So if this is set at the default to scale, there would be something, it would bounce around on the low end of this. However, it's very easy for attacks to generate a lot of traffic, and attacks might be intentional, or it could be just misconfigured things, or it could be somebody, again, I mentioned tunneling. People use DNS tunneling to do things which could result in a big splash of unique recursions, because each one of these tunneling requests contains data that is unique, so it's not going to be in the cache. So anyway, there's a lot of reasons that there could be huge bursts that will expand this so that there is more and more and more. So what will happen as CACHESERVE starts filling this recursion, either due to attacks, or the other thing that can happen is, suppose the network is bad to some part of the internet where there's authoritative servers. And so the authoritative servers don't respond because we're not getting the requests there. Or maybe an authoritative server is broken, and so for popular domains, I mean, that can start piling up a lot of things waiting to be processed. And so this can pile up, and what will happen is that when we reach the maximum, the longest running recursion will just be dropped off of the end. The thinking is that it may never finish, and so and how much is longest running? Well, the longest that CACHESERVE would ever wait for anything, for any single request, is 5 seconds, which is an eternity, of course, in internet time. So 5 seconds, a huge amount of time. CACHESERVE would not actually wait that long for a specific server to respond. It would switch to some of the other servers long before that, but the longest that it would ever wait would be 5 seconds. So you never, so anything that's been sitting around here for 4 seconds or 5 seconds is probably never going to get an answer. So that just gets chopped off, and that way that gives us new room to do another recursion. And there are statistics that will tell you if it's happening. Well, one statistic is you can look at how many recursions are in here at any time. And so we can go back to, if I still have my screen here, back to my resolver.statistics, name equals world, and let's see, I'm going to do all equals true, because I want to see even the ones that are 0. And you can see, so there's all the statistics for this. Let's see. What I'm looking at, and I'm trying to see is here we see some of the interrupted before recursion, interrupted recursion waits. I'll show you what those mean. Dropped recursions, interrupted recursions. These are all the counters that will tell you whether this is happening. I wanted to see the number of current recursion context, and maybe that's on this server. It might be actually on the server. That's a server-wide thing, so that's why it's on there. So server dot statistics and all equals true. This time I'll say Y for yes. And somewhere in here, where is responses, recursion context in use here. This is what I was looking at. So this is on the server as a whole, which is how this is configured. It's all of the caches use a common recursion pool. You can see that this is 0, which in a training lab where I've got a tiny stream of traffic, it's going to be 0 most of the time, because for one thing, the traffic profile is not real, and so there's a lot of queries that are repeated, so things will come from the cache in general, and just the rate of queries is just overall much smaller than you would see in production. And so in the training, let's see, I could try and look again, see if I happen to catch recursion, and that's still 0. So that is most of the time going to be 0, but in production that number is going to be, you would see if it went all the way up to the top to the 25,000. Most of the time it's going to be down here. And those other statistics that I showed you on the resolver, this terminating the recursion is incremented by a counter called interrupted recursions. We saw that was also 0. Well, because in our case, there's nothing in this pipe, because most of the time there's nothing here. So we're never going to see this interrupted recursion be incremented in a lab. Well, at least not in the training, unless you work at it. So the client will know that